On the board right now, you see a diagram of a pulley. That pulley contains a 10-kilogram object on the left side, a 7-kilogram object on the right side. We've dealt with this. We know how to find the acceleration of this system, but that's not the question here today. The question here today is, what's the force between the two objects? In other words, what's the tension in that rope between the two objects right here? I'm going to give you about 5 minutes to see if you can figure out what that tension is, then we'll take a look at it as a class. Ready to take a look here, guys. What's the first thing we got to do if we want to find the tension in the rope that joins these two objects together? Yep. Okay, let's draw them horizontally. Let's pretend it's on a flat horizontal surface. So we've got a 10-kilogram object, we got a 7. That's not an absolutely mandatory thing to do, but I do think it makes it easier to solve the problem. So let's do that. Now what? Now what? Yep. Yeah, we got to find the acceleration of the system. So what we're going to do here is essentially pretend that that's one object, and that one object has a force acting on it to the right. We're going to call it F2. It's equal to 7 times 9.81. I think that works out to be 68.86. Is that right? 68.67. Thank you. And then we've got a force acting to the left on this system that is, we'll call it F1, 10 times 9.81, which is 98.1 newtons. Let's say F net is equal to the sum of the forces. That's F1 plus F2. It means that, what mass do we use there? What mass are we going to use there? We know what mass we're going to use. 10, 7, or 17. Good. Let's use the 17-kilogram mass. Let's find the acceleration. F1 is negative 98.1. F2 is positive 68.67. Look, we're finding acceleration here. That's not what we're looking for, but that's a tool that we've got to get in order to solve what we're looking for. So let's get that. Negative 98.1 plus 68.67 is going to give me 29.43. Negative 29.43. We're going to divide that by 17, and it's going to be somewhere in the range of, I'm going to say 1.6. 1.73, thank you. 1.73 meters per second squared, right? Yes, it would be, thank you. It's negative 1.73 meters per second squared. Good. So that means that the 10-kilogram object will accelerate downward, the 7-kilogram object would accelerate upwards, right? Okay, we're not done, but we're actually done a pretty good part of this question, even though we don't have an answer yet for what we're looking for. What's next? What's next? Yep. Yeah, let's pick a single object and draw the free body diagram for that one object. Now, I don't think there's an advantage of one object over the other here. Typically, what we want to do is pick one of the objects on the end, but you can see that both of them are on the end, right? One's on the left end, one's on the right end. I don't think one's more convenient than the other. Maybe the 10 may be slightly more convenient because it's an easier number to deal with than a 7, right? Easier to do the calculations, but I think that's a pretty marginal advantage at best here. So I'm going to pick that, but I don't think there's a real good reason why we should pick the 10 over the 7. If we do that, we're going to have a force of gravity acting to the left. It's F1. We already said that that was 98.1 newtons. We're going to have a force of tension acting to the right, which is the force of the rope. Right? F2 isn't there anymore because F2 is acting directly on object number 2. So let's analyze that one object. Nathan said a minute ago, F net is equal to F1 plus Ft. F net is 10 times the acceleration we determined was negative 1.73. F1 was negative 98.1. And we're solving for Ft here. So we get negative 17.3, negative 98.1, plus Ft. The 98.1 goes over by adding, and when we do that, we should get 97.8. Is it 80.8? Is that right? 80.8? And that's going to be a positive value, right? We should actually round that to how many digits? Let's go back to our original data. Final answer should be Good, 2. 2 digits. 2 digits here, 2 digits here. Final answer should be 2 digits. So we're going to say 81 newtons. Now it's positive value, which it should be, right? It should be, because the way I had my free body diagram, Ft is drawn to the right. Did anybody do this picking object 2 as your individual object, Luca? Yes, anybody else? Yeah, okay, that's fine. Okay. Your amount of work would be pretty much identical to the amount of work that I showed here, right? Because there's 2 forces acting on each of them, F1 or F2, and then the tension. Now, what did you get for an answer, Luca? Negative 81. Is that a coincidence? No, of course not. If object A applies a force on object B applies an equal and opposite force on object A, right? Good. I've mentioned this before. Hey, if you get a question like this on the tests and you've got time, solve it both ways. Solve it my way using the 10 kilogram object. Solve it Luca's way using the 7 kilogram object. And if you get the same answer both ways, you're right. You did it right. You can be virtually positive you've got the right answer. If you get a different answer both ways, then you can be 100% sure that you have the wrong answer. So try again. You guys comfortable? Good? All right, let's pick up where we left off yesterday then with our whole beginning of the analysis of energy. We defined energy yesterday as the ability to do work. We're not saying that work is being done. Okay, that's not energy. Energy is the ability to do work. Now, sometimes work is being done, and sometimes we're kind of waiting to do work with the energy that we have. If work is being done, then we've got kinetic energy. It's energy of motion. Something's moving. Something's moving. It could be something as small as a molecule inside some kind of material, gas, liquid, solid. It could be something as big as a train rolling down the tracks, or even bigger, like a planet moving around the sun. Kinetic energy is the energy of motion, and everything that's moving has kinetic energy. The kinetic energy of the object is equal to 1/2 mv squared. What's m stand for? That's an easy question. What's m stand for? Mass, good. Mass, a vector, or a scalar? Scalar. And what are the units that we would use for mass here? Jordan? Kilograms, of course, right. What's v stand for? That's the one that's a little bit harder. You guys nailed that yesterday, but a lot of times we get this wrong. What's v stand for? Good, it's speed, not velocity. Speed. Now, is speed a vector or a scalar? Scalar. And the units for speed would be? Meters per second. Good. When we multiply a scalar by a scalar and a scalar again, because it's v squared, we're going to get a scalar. So kinetic energy is a scalar. And the units that we would use to measure kinetic energy are what? Yep, joules. Good. Every single time you calculate kinetic energy, it doesn't matter whether it's for that molecule that's moving around inside a gas, or whether it's the sun moving around within the galaxy, the Milky Way galaxy, it doesn't matter. EK is equal to 1/2 mv squared, and the product that you get is going to be measured in joules, and it's going to be a scalar every time, regardless of the scale. We also talked about potential energy yesterday, the other category of energy, and we broke that down into a number of subcategories. What was one of them? What was one of the most common ones, albeit one that we don't use in Physics 20? Might use it in Chemistry 20 or Chemistry 30. There's your hint right there. What kind of potential energy is it? Chemical potential energy. Chemical potential energy exists in the gasoline of your car. Chemical potential energy exists in the coal that's burned to generate electricity in Alberta. Chemical potential energy is stored in our bodies to give us the ability to move and to talk and to think and to do things. Chemical potential energy is that energy that's stored in chemicals. Another kind of potential energy. We talked about nuclear yesterday, right? We're not going to deal with that in Physics 20 either, although we will take a look at it in Physics 30. Another kind? Wow, what did I spell there? Is that like French or something? Nuclear, there you go. What's another kind? Yep. Gravitational potential energy, and that's a big one for us. We're going to focus on that quite a bit in Physics 20. starting today. So we're going to circle that one. We'll come back to it in a minute. Yep. Elastic potential energy, another big one for us. We talked about that at length yesterday as well. Elastic, sometimes they call it spring potential, because really in the end, whether you've got an elastic that's stretched or a spring that's stretched or compressed, it's really the same thing, right? The relationships involved are exactly the same. Yep. Electric energy, yep. We'll talk about that more in Physics 30. Okay. But nevertheless, it is a type of energy that we can know about in Physics 20. You guys remember the equation for gravitational potential energy? The energy stored in an object due to its height above the surface? Somebody gave me this yesterday. Somebody remembered it from Science 10. Good. EP is equal to mgh. EP stands for the potential energy. M is the mass. G is 9.81. At least if you're on the Earth, G is 9.81. H is the height above the surface of the Earth, or at least the height above something. Potential energy is actually relative. Okay, we say usually potential energy is measured relative to the Earth because objects have the potential to fall to the Earth. But they also have the potential to fall to other things. For instance, my board marker right now is on the desk. The potential energy of that board marker relative to the floor is mg times a height of about a meter. So mg times 1 meter. The potential energy relative to the desk is 0 because it has no height relative to the desk. It has the ability to fall to the ground. It doesn't have the ability to fall to the desk because it's on the desk. Okay, so potential energy is a relative thing. It's measured relative to whatever you want, the floor or the desk, whatever you want, as long as you specify. We'll talk more about that as we do calculations with it. EP is a vector or scalar? Scalar. Every kind of energy is a scalar. What are the units that we use to measure EP? Units, Matt? Joules. Good, joules. Joules for every kind of energy. Every kind of energy is a scalar as well. Elastic or spring potential energy. We got an equation here that we've never seen before yesterday. EP is equal to 1/2 kx squared. You remember what k was? Joseph? Yeah, it's the elastic constant or the spring constant. And that elastic constant or spring constant is essentially a measure of how stiff the spring or elastic is. The stiffer it is, the more ability it has to hold potential energy. The harder it is to stretch as well. The bigger K is, the harder it is to stretch. But the more energy it has the ability to hold. So the stiffer it is, the bigger the value of K, the more energy it has the ability to hold. What's X stand for? This was the tricky one. We used the elastic, the little hairy elastic yesterday to show you what little x is. It's a little bit confusing here. Yep. Good, it's the displacement of the spring or the elastic, but there's two displacements that we can talk about here. One is the displacement of the spring as I throw it across the room, okay, the movement of the spring. The other displacement is the amount the spring is stretched. Which one are we talking about here? Yeah, how far it's stretched or compressed, right? Squished. We don't want the movement across the room. That would be delta D displacement. Okay, the amount that it's stretched or compressed would be X displacement. And what units would we use for X? Displacement. Even though it's a different displacement than we're used to talking about, it's going to be the same units in meters. Anybody remember K? What units we use for that? Good, newtons per meter. You'll see a little bit later on why it's newtons per meter. EP is joules, and of course it's going to be a scalar. Right? That's where we left off yesterday. Let's take a look at our first energy example here. It says on a highway, a car of mass 1,200 kilograms is traveling at 20 meters per second. Has a kinetic energy equal to a loaded van of mass 4.8 times 10 to the 3 kilograms. What's the speed of the van? This is kind of a tricky one to start off with. A little bit of a tricky one to start off with here. Maybe they should give us one that's a little bit easier, one that says, like, look, here's the mass, here's gravity, here's the height, or here's the mass, here's the speed, find the kinetic energy. They're telling us something else here. They're saying, look, you got a car here with a certain speed, and we got a second vehicle with a different speed, and we're trying to find out what it is. Whenever you come across a question, how many people are looking at this question thinking, I'm not sure exactly where to go with this? Hands up if you're not sure where to go with this. That's okay. That's okay. It's a first example, right? That's why we do examples. But I want you to always remember this. And when you encounter something like this, you're not sure exactly where to go with it, do something that's valid. I'm not saying here that you want to, let's divide the mass in half and say I got the answer. Well, that's not valid, right? We all know that that's not what's going to happen here. But we know that this car has kinetic energy. Why don't we find it? What's it going to do for me? I don't know, but it's something. Okay, if you're one of the half of the class that put up your hand saying, I'm not sure exactly where to go with this, then just do something with the kinetic energy of the car. Instead of calling it, you know what, I'll call it EK, but I'm going to label it car here, the kinetic energy of the car. It's 1/2 of mv squared. It's 1/2 of 1200 times 20 squared. 20 squared is 400 times 600 is 40,000 joules, I believe. Okay, that's not a final answer, so I'm not going to round it to the right number of digits. Have I got what I'm looking for? No. Have I got something? Yes. Is it going to help me in what I'm looking for? Maybe. Now let's look at this. Now let's look at this as saying, hey, I know the kinetic energy of the car. Read the next sentence. Read the next sentence. Kinetic energy of the car is 40,000 joules. It has a kinetic energy equal to the kinetic energy of a van. So what else do we know? What else do we know now besides the kinetic energy of the car is 40,000 joules? Yep. Good. Here's the van, and its kinetic energy is 40,000 joules. So we know two things that we didn't know before. Maybe we didn't know why we were solving for kinetic energy of the car. Okay, but we got it because we could. And now we have the kinetic energy, miraculously have the kinetic energy of the van as well. All right, we want to find its speed. Let's just set that equal to 1/2 mv squared. Let's say, this is kind of tricky to rearrange, actually. Solving for v. We're going to say, we're dividing by 2 here, so we'll take the 2 up by multiplying. It becomes 2 EK. Or you could say EK divided by 1/2, either one. Yep. Let's divide that by mass, because mass goes down by dividing. And then we're left with v squared is equal to 2 EK over m. How do you get rid of the square there, Tegan? Good. Square root both sides. So we end up with this. It becomes the square root of 2 times 40,000 divided by the mass of the car, of the van, sorry, is 4.8 times 10 to the 3 kilograms. We end up getting 4.08, or we're going to say 4.1 meters per second. Hey, I got a question for you. Sam, question? I think it's 40. Oh, did I? Oh, yeah. Yeah, right. 20 squared is 40 times 600 would be 240,000. You're right. Thank you. Doesn't change a whole lot in there except the answer here. What does the answer work out to be? Is it 10? Okay. Thank you, Sam. Hey, you notice anything with the speed here that kind of strikes you? It's an even number, right? It's not 10.3, it's 10. I should have known that, actually. I should have caught that when I looked at the final answer. Because there is something kind of special to that speed. What do you notice about that speed relative to the initial speed of the car? Yep. Good. So the kinetic energy of both of them are the same. If the kinetic energy is the same, then the one that's heavier has to be moving slower. How much slower? It's 1/4 the speed, isn't it? It was going, sorry, half the speed, I mean. It was going 20 meters per second. This guy's going 10 meters per second. If we're quadrupling the mass, why isn't the speed going down by a factor of 4? Why is it only going down by a factor of 2? No, not because it's half, but you're on the right track. It's not because it's 1/2 mv squared. It's because it's 1/2 mv squared. Right? It's the v squared that's the important thing there. I don't expect you guys to necessarily catch the mathematical relationship there, other than what Joseph just spotted, the fact that kinetic energy is the same, mass is bigger, speed will be smaller. If you understand why it's exactly half the speed, that's great. If you just understand why it should be smaller speed, that's fine too. Okay? That makes sense, guys? It's a tough one to start off with, eh? It's a tough first example question. There's pros and cons to that, right? A little bit more challenging to start off, but the pros to it are that, hey, the other questions should seem easier now that we've started off with a hard one. See what we can do with these 3 questions, please. Before you do, you know what? Before you do, I want to review just a couple of small things. First of all, we got to be able to rearrange that equation for kinetic energy, right? Let's spend a minute just rearranging it for these 2 variables. Solve for m. Well, let's take the half over by dividing, or you could also take it over by multiplying by 2. Same deal, right? Solve for m. Say 2ek over v squared, or you could say ek over half v squared, same thing. Solving for v, well, we can take the half over by dividing or over by multiplying by 2. Let's say that it's 2ek, take the m over by dividing, and then we're going to square root that. So m is 2ek over v squared. V is square root of 2ek over m. The only other thing that I wanted to remind you of here is this. It's been a little while since we've converted to meters per second from kilometers per hour, right? Anybody remember how to do that? Yep, Sam? Good. So it's 80,000 divided by 3,600, because there's 1,000 meters in a kilometer and 3,600 hours in a second. I'm sorry, 3,600 seconds in an hour. You know what I mean, right? Good? All right, I think you're okay to tackle these now. Let's see what you can do, okay? Yep. Yep. Let's take a look at number 3 here. It says a skateboarder with a mass of 65 kilograms increases his speed from 1.75 meters per second to 4.20 meters per second as he rolls down a ramp. What's the increase in his kinetic energy? The word increase means change, right? What's it changed by? Okay, if my mass changed by over Christmas when I was eating junk food like crazy, if my mass changed from 68 kilograms to 71 kilograms, then my increase in mass would be 3 kilograms. My delta M, my change in mass, would be 3 kilograms. Okay, here we're looking for the increase in kinetic energy, or we're looking for the delta kinetic energy, the change in kinetic energy. Does that make sense? All right. To find delta something, we have to say something final minus something initial. So we're going to say EKF minus EKI here. Now, the final kinetic energy is 1/2 mvf squared, and the initial is 1/2 mvi squared. Can you cancel out the m there? Same mass, both terms, right? Can I cancel out the m? Sam? No, you're right. You can't. It doesn't have to appear in both terms on the right side. It has to appear in every term on both sides. You can't cancel the mass here. What we're going to say here is 1/2 of the mass, which is 65, times 4.2 squared minus 1/2 of 65 times 1.75 squared. Now, I suspect what a lot of you guys are doing right now, if you're making a mistake, is forgetting to square the v. Hey, that's a pretty common mistake, is forgetting to square the v. When you do this math, if you don't forget to square the v, you should get 474 joules. Make sure that you either get this number on your calculator, then subtract them, or get this number and then subtract brackets. Do all that work. Okay? Don't go subtract and then do a bunch of multiplication without brackets there. Does that make sense? All right, I want to show you something that I'm thinking some of you may have tried, but you got the wrong answer. And I want you to tell me, own up to it if you tried this, okay? If delta E is final minus initial, and it's 1/2 mvf squared minus 1/2 mvi squared, then couldn't we just say 1/2 m times delta v squared? Right, isn't that the same thing? Looks like it. Let's see what we get, though. If we do that, we'll say 1/2 of 65 times, what's the change in speed? 4.2 minus 1.75. That's going to give me 2.45. Okay, I don't know what we get when we do that math, but it's not the right answer. Anybody try that? Okay. It seems like a logical thing to do, doesn't it? Yeah, like, I'd be surprised if it was only you, to be honest, that tried that, because it does seem like a very logical thing to do. If I was in grade 11, I probably would have tried that. If I spotted it, that is. I probably would have tried that. Why does it not give us the right answer? Why does it not give us the right answer? If we changed the mass, that would have worked. If we had to change the mass but left the speed the same, that would have worked. But changing the speed, doing it this way, doesn't work. How come? Yes, because it's squared. Okay. Anytime you do something like that, if you're squaring the variable, you can't just arbitrarily stick a delta in there. Now, if you're not squaring it, you could. If there was a change in m, you could say 1/2 delta m times v squared, but not with the v, since it's squared. Okay, if that doesn't make sense to you, just don't even try it for anything. Just do it the way we did it the first time, okay? Oh, absolutely. Absolutely you can. Oh, didn't you? Must have made a mistake then. Well, I wouldn't say failure. Let's talk about gravity again for just a moment here. Gravitational potential energy we defined as the energy stored in an object due to its height. Height above whatever we want. It's relative to something else. Example I gave you before we did the practice problem there. We said the potential energy of the pen relative to the desk was 0 because its height relative to the desk was 0. Relative to the floor, it was something because it had a height relative to the floor. It had no potential to fall to the desk. It had potential to fall to the floor. So it had potential energy relative to the floor. We can define our height relative to whatever we want, but a couple things. A, we've got to be consistent within the problem. So if we're defining it relative to the desk, that's fine, but stick with the desk throughout the whole problem. And B, make sure you specify what it's relative to. Relative to the desk, relative to your hand, relative to the floor. Specify what it's relative to. If you don't specify, we're going to assume you mean relative to the ground. Another example, 6.3 on page 298. It says, this shows a toy car track set up on a tabletop. We want to know the gravitational potential energy of the car, which has this mass, relative to the floor. And we want to know what the change in gravitational potential of the car is when it arrives at the bottom of the hill. So let's worry about one thing at a time. What's the gravitational potential energy of the car? And Nathan, this is where you got to read, right? relative to the floor. We got a couple of different heights here. Okay, we know that the height of the table is 0.950. We could find easily the height of the toy car above the tabletop, but we also have the height relative to the floor, 2.15 meters. Which one do we want here? 3 different heights. We want this one. We want to find the height, the potential energy relative to the floor, so let's use the height relative to the floor. We could just as easily have asked you in this question, what's the potential energy relative to the tabletop? In that case, we would have had to use this height, the red height here. Okay, it's not what was being asked, but it could have been just as easily. Let's say EP, for question A, is equal to mgh. The mass, of course, is 0.0250, regardless of what you're trying to find the potential energy relative to. G is also 9.81, regardless of where your reference point is. But the height is what you got to be careful of. The height here is 2.15 meters above the floor. Don't use the height above the table. Don't use the height of the table. Use the height from the top to the floor. You get 0.025 times 9.81 times 2.15. I get an answer of 0.52729 joules there, which I'm going to round to 3 digits. Okay, 3 digits here, 3 digits here. Does anybody know why I left the unrounded number there first? Why I wrote that down, unrounded? I could have just looked at my calculator and rounded it in my head, right? And not even written down this number. Yeah. Yeah, if I need it for B, I may need it for B. If I need it for B, then I don't want to use the rounded number. I want to use the unrounded number, right? So I wrote down the rounded number because it's a final answer, but it may become in question B not a final answer again, so I may need the unrounded number again. I may not, but I want to have it ready just in case. B says, what's the change in potential energy of the car when it arrives at the bottom of the hill? Well, delta EP is equal to EP final minus EP initial, or Bree and just about everybody else in the class might want to do this as calculating the final potential, calculating the initial potential, and then subtracting them. Okay, whatever makes you feel good, guys. It's the same thing, any way you look at it here. The final potential relative to the relative to the floor is mghf minus mghi. We're going to say 0.0250 times the final height, which is 0.950. Times 9.81 times the final height. Minus, well, we already calculated mghi, 0.52729. When I do that, I get negative 0.294 joules. Couple of things that I want to point out here. First of all, this is a question where I could have actually said delta EP is equal to m times g times delta H. I could have did it in one step there. I couldn't have done that up there with the kinetic energy question, but I can with the potential. How come? Because it's not squared. The H isn't squared. Now, if that confuses you, don't worry about it. Don't even bother trying to do that. Now, the second thing I want to draw your attention to and ask you about is the negative there, negative 0.294. Didn't we say yesterday and earlier today when we were reviewing that energy is a scalar? Is it always a scalar? Yes, it's always a scalar. So where does that negative come from? Yeah, it doesn't mean down in this case. Usually a negative means down for us, right? Positive means up. A negative here for a delta E doesn't mean energy down. It means a loss of energy. You have less than when you started. That make sense? Finally, one more thing that I want to ask you about. What if I had picked not the floor as my reference point, but rather the tabletop as my reference point? What if I had to solve for the initial potential right here, the final potential right here, subtracted them, what would I have gotten? Joseph? No. Still would have been a loss of energy. Would have been the same answer. The energy relative to the floor is different than the energy relative to the tabletop, but the change in energy isn't. You lose a certain amount of energy regardless of what your reference point is. Okay, does that make sense? So for B, it didn't matter what your reference point was as long as you were consistent and used the same reference point, the tabletop or the floor. I just used the floor because that's what I had done in question A. All right? Is that okay? All right, let's take a look at those 3 questions, please. On page 298.